Hey, Sean, how's it going?
Good, Peter. Here we go.
Yeah, let's do it. Today we're talking about building science and facades because we're from Oculus, building science and facades. We might as well say what our job is, what we do, the parts of the buildings that we care about, and how it all fits together. So
Yeah.
I guess let's get into it.
Yeah.
What's building science?
Yeah. That's a really good question. It's new.
A lot of things.
It's new, right?
Sure.
When would you say building science started?
I would
First person
say,
who called himself a building scientist.
Ooh. Okay, so I was going to say building science started from like the beginning of time, probably, or the beginning of buildings at least, because it's always science.
Physics has been around forever. Yeah, okay.
Exactly. But if we're talking about like who called themselves the first building scientists, maybe the 60s or 70s in Canada, possibly?
Yeah, I was going to say maybe the Passive House in Saskatchewan.
Oh, could be.
Around that time, like 50s.
Sure.
What was the name of that place? Can't remember
off the top of my head, but it was called something. I wish we had a background person to kind of like Google it for us and put it up on screen. If only.
It's called Saskatchewan.
Sponsor us and we'll do that. We'll have a guy
we get a guy
off camera.
Yeah.
But anyways, yeah, building science. So yeah, probably started in the 50s. Once we started, I guess, trying to modernize, trying to use different materials.
Well, probably started when things started going wrong.
Sure. Yeah, right? That's usually how building codes are changed. Yeah. Things go wrong. So
that's where structural engineers probably came from.
Sure.
Every discipline's probably come from that, right?
Actually, yeah. Like something goes wrong, and then the first person to figure out how to make that not go wrong, they're the first scientist or the first engineer for that thing, I guess.
Yeah, or you're like, man, I'm tired of our houses looking ugly. I wonder if it's someone who's really good at designing houses that look good.
Sure.
Yeah, there's an architect guy.
Yeah. I mean, like, they're good at making things look good, but yeah. The building science kind of goes a little bit deeper than that, right? It's kind of how all the components work together, how the assemblies work together, how the inside air is quality and temperature and humidity wise. There's just so many things that kind of...
it's interesting that we call it building science when there's actually science in every part of engineering.
That's valid. That is valid.
It's really what we do is enclosure engineering.
Sure. Some people call it building science engineering, enclosure engineering, envelope engineering.
Yeah.
Facade engineering, I feel like, doesn't really capture the whole thing.
If you ask the people that came up with envelope engineering, they're upset that they did.
Really?
They'd rather it be called enclosure engineering.
That's fair, because people think like letters, envelopes, like, mail and stuff like that.
True story. I had a young engineer at my office I was supervising.
Sure.
And they went back for Thanksgiving, where a family get together.
Sure.
And they were talking with their uncle.
Okay.
And they said, "What are you doing now?" She's like, "Oh, I'm an envelope engineer." And they got into a 5-minute conversation, like, "Wow, you really need an engineer to like get the folds right, and like the adhesive, like
the glue has to taste right when you're licking it, Maybe that's what they're engineering.
Awesome, right?
Getting rid of the paper cuts.
Oh yeah,
engineered envelopes.
There probably is an engineer that does
I'd assume it's like a paper engineer or like an origami engineer, maybe.
For sure.
Materials. Yeah, that makes sense. But the envelope that we talk about is more about the building envelope, which is, all the things that separate the inside from the outside. The roof, the windows, the insulation, cladding, sealants, I don't know. What else is there? Membranes, all kinds of different things and how they all connect to each other.
So many things, right? It's that's why it's kind of fun, because you have to know a whole bunch about you have to know a little bit about a whole bunch.
Yes.
Someone I think it's BC, has a really good definition of what the building enclosure is.
Okay.
I'm going to paraphrase it, but it's the parts of the building that separate the inside from the deleterious effects of the outside.
Oh, interesting. Okay.
It's very well worded, and I'm kind of paraphrasing it there, but
But the key thing that they're centering in on is that the interior is a certain temperature, a certain requirement for comfort. Mm-hmm. And you're also trying to make it so that the exterior, which has, a lot of UV from the sun, rain, wind, etc., none of that is going to break anything or damage anything on the inside.
Yep.
Which is, I think, a very interesting and, I guess, decisive way to go with it, because it means that what we're trying to do is safeguard the inside, make sure it doesn't start to deteriorate. The people inside are comfortable. It really puts that into perspective as opposed to...
I like the term protect and separate in there.
Sure, yeah.
I'm not sure I said that before, but I'm pretty sure it's protect and separate.
Yeah.
Which reminds me of protect and serve.
Sure, a little bit. The walls are the police of the house.
The police of the house, yeah.
Sure.
And the weather is the bad guys. Keep them out, right?
I see. Okay, fair.
Yeah.
It's a fun way of thinking of it. I wonder if there's going to be like a cops show that shows up and, the building.
Are you foreshadowing a new episode?
Maybe, or like an animated series. I'm thinking, for kids, make it simplified. But anyways,
yes.
Building science, the interior, the exterior. We're trying to make the interior a nice, comfortable, healthy temperature. Keep the outside, and make sure nothing gets damaged in the process. When do we usually kind of get dragged into a meeting for a project, or when do we start on a project? And is that the right time, the wrong time?
Way too late.
Way too late usually.
I've never been in a project too early.
Yeah.
Never once have been like, man, you don't need this yet.
Yeah. Like there's been times where I've been on the project fairly early, and then we do a bunch of work really early, and then we don't do a bunch of work for a while because everyone else is sorting their stuff out after they've heard from us, I guess.
Yeah.
But that's not too early.
Well,
it's the
sometimes,
right time.
here's a good example of when it's too late.
Sure.
So classically, we get brought in once the structure is half done.
Sure.
And maybe the architects picked the cladding types, and the building kind of looks roughly what it's going to look like.
The shape,
right?
the windows, they're all kind of in place.
And so we get brought in, and something that's not commonly thought of in building science is movement. Movement of the building.
Yeah.
So we get brought in at, just an example, hypothetically, you're brought in on a project, and the structure is quite flexible. It moves quite a bit.
Sure.
And it's got brick cladding, which does not move a lot.
Sure.
Now you've got this clash between cladding and structure.
Super flexible versus super rigid.
Yeah.
And now you have to make it work.
And now you've got a really awkward interface between those two things. Yeah. Whereas if you're brought in before you start putting cladding on the building, or before they start designing the structure.
Yeah, before major decisions have been made.
You would point out, like, either you really want brick, in which case make your structure quite stiff, or maybe you don't want brick so much, but you can have a lighter structure.
Sure.
That's an example of how we would have some advice early on that would steer you to an easier solution.
Yeah, and especially early on in the project, it's easy to say, oh, we have a very flexible building, you want a very rigid cladding, maybe we choose a different cladding, or maybe we stiffen things up. And people aren't doing rework, we're not redoing designs, it's already kind of not really decided, and then we decide and then kind of go from there. And it kind of makes things cheaper, easier, faster, more efficient during that design process.
The other way I've described kind of what I do for so if I get the elevator pitch, someone asks what I do, I tell my design roofs, walls, and windows to keep the outside out and the inside in. Yep. But if they go a little deeper, what does that mean?
Yeah.
I usually tell them that I help architects make sure that the project or their vision actually functions.
Sure. That's definitely a possibility,
We are like the architect. I'm not an architect, and I actually considered architecture, and I don't like drawing. I'm not that creative.
Same. I did the exact same thing. I'm like, do I want to make a portfolio? Not really. No, I'll do the math.
No, but there's lots of people that are really good at that creative aspect of it.
Absolutely.
And then a lot, what you're seeing in architecture now is you've got creative people which draw really beautiful buildings, and you've got the other side of architecture which is really technically focused in detailing and drawing.
Sure.
And that's the side we work in.
Sure.
The technical details, the nitty-gritty, the materials, the science.
Coordination between different disciplines
Yeah.
Yeah. And I find that when I'm describing it to an architect, I usually say the exact same thing that you say first. And then if they start to dig in, another thing that I'll mention is that we allow the architects to do whatever they want, because it's kind of the baseline kind of assumption is we go to E2AS1, take the prescriptive details, copy paste, try to massage them to make them work. But what we do is allow people to use whichever assembly, whichever component, and detail it in a way that looks a certain way, and we make sure that it's still going to be durable, robust, watertight, shed all the things away, but we don't have to follow those prescriptive details. We get a little bit more flexibility, which is pretty cool.
For those of you that aren't in New Zealand and with the New Zealand Building Code, E2AS1, something you'll hear a lot on this podcast. It is a prescriptive method of detailing the outsides of very simple houses.
Yeah. Very similar to Part 9 of the building code in Canada.
Yeah, Part 9 is the closest example. I'm sure every country has some sort of prescriptive details. Australia's got deemed to satisfy solutions. Yeah. Everyone's got their, I think the performance-based building codes is the utopia of building codes.
Yeah, it's great.
And then the first thing every builder does is say, I don't know how to do this. Just tell me what to build.
Yeah.
And so you end up with prescriptive requirements. Now, what's happened in New Zealand and elsewhere is those prescriptive details start to creep back into this is the way you have to build things.
Yeah.
And what Peter is sort of alluding to is that we work in the first principles performance-based area of the code. So
Correct.
We're not bound and constricted by bad detailing from the prescriptive side.
Yeah.
We got a lot more freedom to sort of do and explore other materials, other junctions, details.
Different overlaps, different heights, different slopes, things like that. Because I mean, like, there's nothing inherently really specifically wrong with the acceptable solutions. I mean, I'm overstating it a little bit, because the acceptable solutions I find are... I'm going to back up for a second. You mentioned the performance requirements of the code, which I think are amazing, because as long as you meet the keep water out of the building and keep it from damaging anything, you meet that and you can prove that, you're good to go. Do whatever you want. Yeah. But with E2AS1, the prescriptive details, a lot of times they lack nuance because they're kind of drawn for the lowest common denominator, for the worst material or component that they're putting in there, just in case the contractor doesn't build it properly. It's kind of a fail-safe.
It's a lot of conservatism in those prescriptive requirements, which you're not sure how people are going to interpret it and build it.
Yeah, which is good for certain situations. But if you want a very specific look, then maybe those details aren't quite.
If you're trying to give 40,000 people in one country one way to build things, you keep things very conservative, very simple, and you don't change much.
Exactly.
And you don't change unless something breaks. And potentially we've broken some stuff recently with.
Yeah. But when other parts of the code get updated, the prescriptive details that were, I guess, drawn up before, like at an earlier time, sometimes they become less relevant, or they kind of clash with the new parts of the code.
Or people don't understand why they worked in the first place.
Yeah, exactly. And they just assume, this is how it has to be, without knowing the reasons why behind it, kind of.
We'll do a whole episode on roofs and ventilation, I'm sure, because it's very complicated.
Yeah.
It is ever-changing.
Yeah.
And ever-changing very quickly. Like in the last... So the problems happening in coastal Canada and Vancouver climate, those are 2010 when those started popping up.
Oh, absolutely.
That's 15 years, and it coincides with the insulation upgrades. But
I think that kind of segues really nicely into the other thing that we worry about that not a lot of people are necessarily aware of yet, and that's the interstitial condensation risk, and having... adding extra insulation to an assembly that you've been using for the past 30 years, but you increase that insulation, maybe some weird stuff happens. Maybe some weird heat flow things and moisture flow things happen, and then you start getting condensation inside the walls. Everyone knows about dew points, but do we know how to avoid dew point issues and condensation issues in the walls?
I just want to clear the air on dew points, by the way.
Sure, let's hear it.
I hadn't heard of the term dew point the way it's used here before.
Same.
Right? Dew point is like a dew point temperature.
Yeah.
And then you have a cold thing that reaches that dew point temperature, you get condensation.
Like basically you have a box of air, it's at a certain temperature and relative humidity, and you cool it down to a certain temperature, and then you see water.
Yeah.
That's the dew point.
Whereas here we talk about the place in the wall that is at 12 degrees or whatever the
dew point temperature is, yeah.
But I actually love the term dew point now.
Sure.
Because it's inside your wall. Yeah. This is the point where the dew is going to be.
Uh-huh. It's simplified, but it actually makes... I used to kind of think that it was oversimplified, but it just makes sense to people who don't necessarily care about condensation, really.
It's easier to talk about.
Yeah.
Rather than talking about this is the temperature at which the dew point would be reached, and it's very
for this temperature and this relative humidity. Yeah, it gets too complicated. Whereas you say the dew point happens in the wall, everyone gets that. Cool. Let's not do that.
Yeah, that's great.
Yeah. But yeah, that's kind of something that is less, I guess, known about. E3 is the code clause here in New Zealand. In Canada, most of the prescriptive details have kind of sorted out the interstitial condensation issue, because there's been a lot of problems that have happened in the past because of the fact that it's so much colder outside in a lot of places in Canada. Those dew point issues or condensation issues show up faster. So I feel like a lot of things have kind of mostly gotten sorted out, but like you mentioned, from 2010, we're still seeing some issues, especially in the West Coast.
Because we're changing things, right?
Sure.
Right, you've got this assembly, and let's say you build that. Everyone in the country builds that same assembly, for a decade, and they're like, hey, it seems to be working. Let's keep doing it. And then someone else from a different part of the code, different part of the industry, is like, let's add insulation into this. Let's add ventilation into the space, without understanding what knock-on effects it has. Like you've
got to balance everything.
You've upset this was very precarious balance to start with. You've done this. And then you probably have a decade of failures and you go back to something that works and then use something else. And
I think the fun thing, and when I say fun, I'm being a little bit facetious in that, the fun thing about condensation issues is that you don't necessarily notice until 5, 10, 15 years down the road, because you might have that condensation happening inside your walls, inside your roof space, places where you can't see, and it takes a while for the condensation to build up so that you can see it on the inside. You'll start to see staining or mold or start to smell it maybe.
You're talking about the condensation turning into a consequence.
Correct.
Matters. Yeah.
Because sometimes you'll have condensation in the walls, the sun comes out, it dries out the wall, you're all good. Like there's no problem. But if it's going to be a problem because you don't have that drying cycle and it's just constantly accumulating water, you'll start to see that problem in 5, 10, 15 years. Sooner if it's colder outside, later if it's not as cold outside, sooner if it's humid, less soon, later if it's not humid. So
so we probably do an episode on condensation modeling too.
Sure.
There's a lot to dive into there, but what I find interesting in the modeling side is you've got a wall, you've got a roof, you're trying to predict will condensation happen in that.
Sure.
When you do a model, you don't know what the weather's going to happen. What weather's going to happen 10 days from now.
Sure.
So you can't predict 10 years from now what the weather's going to do.
Sure.
On any given day. So what you have to do is create a model year, which has some fluctuations based on averages. Which
basically simulates the conditions of what a year would most likely on average be.
Yeah, but your actual is going to be different than that.
Sure.
You cannot predict what it's going to do.
Yeah.
So your model is inherently, it's called stochastic variables.
Sure. Yep.
So you are modeling something based on your best guess, but you know it will be wrong.
Yeah. And you're just trying to get like an indication of how wrong, how right, how well this is going to work or not kind of thing? Or
I don't even think that if the model says good, that it's good. Or the model says bad, it's bad. What you can use models to do is say this model is bad, this one is badder. Or this one is gooder.
Comparing relative risk, I guess.
Relative risk,
Sure. Yeah. And I mean, that's kind of part of the conversation that we have every day, that, people have been building a certain way for a certain amount of time. There's quote unquote never been any problems, but it also depends on what people's expectations are, I find. And that's a lot of the conversations that I have when I'm talking about building science and in these project teams. Like, what are we expecting? Are we expecting the basement to be dry, or are we expecting it to be wet? Are we expecting the interior to be a nice, consistent, comfortable temperature, or are we kind of expecting it to fluctuate with the seasons? Like, what are we expecting? And then once we've kind of, I guess, agreed on those expectations, then we can design to meet those expectations. But
yeah, you have to agree what good looks like.
Sure.
Right? The building code is the worst thing you can build.
Legally, the worst thing.
It's like the worst building you could think of.
A lot of people think of the building code as this like shining, if I do the building code, it's going to be great. But it's literally the worst legal thing that you're allowed to build.
Yeah. I think we've come a long way on that here. I think people recognize that building code is not great.
Sure.
So then you talk about, what does good look like?
For the record, I just want to repeat again. It's not the building code that's bad. It's the acceptable solutions that generally kind of fall apart.
Yeah.
The prescriptive stuff the performance requirements are pretty good.
There's some parts that are good.
Yeah.
I think fire's come a long way.
Sure.
Pretty robust. It was not great 10-ish or 8 years ago when I got here, but it's come a long way. Structure seems to be at the forefront of a lot of things globally.
Sure.
The seismic code here is pretty advanced.
Once again, for good reason, because bad things happen, and then you fix the code.
Yeah.
That's what happens.
I was back in BC in 2024.
Sure.
There was a 4.6 earthquake that happened. It made the front page of the news.
Oh, wow.
I Googled how many 4.6 earthquakes were in the last 30 days in New Zealand. It was like 42 of them.
Oh my God.
It's like
different worlds.
Every day there was an earthquake.
Yeah.
The big one will happen in BC.
Sure.
And then there'll be a lot of engineers from New Zealand going to BC to go and fix buildings.
The same way that a lot of BC engineers are coming here to fix the condensation issues and things like that.
There's a healthy amount of us here, yes.
Yeah. It's
they all seem to work at one place. But
a little bit, yeah. It's strange how that works. But I guess it's a little bit fun. But yeah, building science, I think it's this growing thing. We're not quite recognized by Engineering New Zealand yet. I'm not sure if even our engineering societies in Canada, do they recognize building science, building envelope as a specific category?
The industry in Canada has been decades
old,
right? It was late 80s, probably Ontario with some building failures, and building science became a thing,
Sure.
and Waterloo started teaching people about it. And
Sure.
so it's been, several decades of establishment in Canada. And it's really interesting. There's, hundreds of building enclosure engineers in Canada. In BC, of hundreds.
Sure.
In New Zealand, there's probably 30.
Yeah. And that's like if you're counting everybody.
I'm counting facade engineers in that too.
Yeah. And also
Yeah.
people who aren't necessarily registered as a CPENG or Auckland Council or anything like that. It's like everybody working on this.
That's like everyone.
Junior,
like,
senior, whoever.
Maybe 50 to 100 people that are in our like enclosure engineering discipline.
Yeah. But it's growing.
BC and New Zealand are similar size.
Yeah.
5 million. So
in terms of population, yeah, true.
population, climate's not far off. It's a little bit different. So it'll be, if you guys don't know that we're mostly a New Zealand company, but just starting a Canadian branch in 2025. So I'll be in the Vancouver area and doing what we're doing back there with my folks.
Yeah. It'd be nice, I think. It's like you said, it's a very similar climate. I feel like Emily was mentioning something about it rains more spread out, or no, more in the winter in Vancouver. Like you get very little rain and then you get a lot of rain during the winter, whereas here it's more spread out.
Yeah, it's almost the same amount of annual and rainfall. What we notice in New Zealand, and Auckland specifically, is the rain comes really hard and heavy fast, and then the sun's usually out in between.
Yeah.
In Vancouver, you get little drips and spits of rain for 8 months.
I see.
That accumulates to the same thing.
I see. So I mean, like same concepts. You just have to think about, the wetting drying cycles. They're a little bit different. The temperature's a bit different. Vancouver's slightly colder than Auckland, but maybe more similar to other places around the country down here. But yeah, building science is important and it's becoming more, I guess, popular, more talked about. In terms of when we first got here, I think there was very little, activity in the building science space here in New Zealand. And I feel like we've made a big kind of dent. How far off are we from fully understanding everyone gets it and we start building things really properly without having to discuss?
I would clarify something you said. I think the building science in New Zealand was brands.
Sure.
And give brands some credit. They've actually got some really good research that's been done there over the decades.
Absolutely.
Our misplaced frustration was that science wasn't getting into practice.
Correct. I've read so many studies and it's like, wow, this is the science behind it. This is what works. This is what doesn't. But yeah, it never transferred into the code or into, standards, let's say, or maybe little bits and bobs. But
so I would say that's probably our biggest contribution in the last 7 years for you, 8 years for me.
Yeah.
Is getting a lot of that. It's really easy to say, here's the science done by a government-funded, New Zealand-specific, trusted institution.
Yep.
We should do that on our buildings too.
Mm-hmm.
That's a better message than,
Yeah, I think it's, I've always said that they do really great research, but it just hasn't translated into things. And so, that's what we're trying to do. We're trying to fill that gap. That's why we're here talking on this podcast and putting resources on our website. It's to kind of bridge that gap. We've seen the research, we've seen the science. Let's build better. Let's use that information and make better designs, right?
Yeah, really. Yeah.
I'm not sure if there's anything else we can say about building science, but I think I think we've covered pretty much all of it.
I think probably the thing we haven't touched on, which is it's in the title, is the science part.
Sure.
The science part being that there's a scientific method of having a hypothesis, creating some sort of test to test that hypothesis, seeing the outcome, blah, 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 blah.
Sure.
And so when we're looking at buildings and enclosures, there is sort of what the standard might say, or the common practice might say, or acceptable solution, whatever it is.
Sure.
There's
the way that's always been done.
Yeah. There's also a whole gigantic body of PhD students and master's thesis that have looked at these issues.
Each one individually, probably to the most detail that you could ever, imagine.
Without limitation, I think every single part of the codes I look at and standards has some sort of missing element to it.
Sure.
Which when you actually understand the science behind it, then you can actually make really robust decisions. And maybe you do end up back at what you always do, but at least you got there from an informed way.
Yeah.
Rather than copying, pasting, and hoping it continues to work.
Yeah.
You don't know what's changed in there.
Well, that's the thing. Like everything always changes. There's new materials being released, different ways of building, different speed, different processes. I don't know, modularization, stuff like that.
There's another good example on that.
Oh,
yeah.
Let's hear it.
Fiber cement claddings.
What about it?
So fiber cement claddings, they're a mixture of cementitious and wood fibers, mash them together, bake them kind of thing.
Cement binder kind of thing.
Yeah. So they're pretty ubiquitous around North America, Europe, everywhere.
Yep.
We've got it. One supplier, they started getting into more sustainability aspects, started looking at fly ash.
Okay.
There's multiple suppliers, not just one.
Sure.
So they started using more fly ash byproduct as filler into these materials.
Sure.
Which is regarded very similar as cement.
Sure, because I mean, like, use that as an admixture for concrete, so you could do the same with fiber cement. I guess,
reasonable theory, right?
Sure.
Issue was that fly ash causes more thermal and moisture expansion than your non. And so now you've got a product that's been used over and over and over again. It's been working on walls, and now suddenly it's starting to crack and expand.
They changed the formulation.
Not understanding the chemistry behind what's gone into that.
And you're talking like those are the ones where, because I've seen studies and I've spoken to other engineers back in Canada that are doing investigations on this fiber cement, and a lot of them have these little microfractures around the fixings and things like that grow over time because water gets in there, freeze thaw, pops it off. This is what you're talking about? This is the fly ash thing, or are they kind of two separate things out of curiosity?
Well, I think you talk about changing chemistries and changing materials.
Sure, okay, fair.
You don't always know what the byproduct that's going to be.
Very fair.
And that's sort of the science part of things is what should have happened is
testing the hypothesis.
We've got a hypothesis that if we add this, make this change the material, we'll continue to get the same results.
Sure.
And it's not always true.
Yeah, sometimes a bunch gets put on a bunch of buildings and then weird things happen because maybe it was designed in a certain climate in a certain country, gets shipped to a different one that's slightly warmer, slightly colder, slightly more humid, slightly drier.
There's lots of variables that go into it. But I guess probably the underlying thing is we've got a scientific process and a way we could go about proving some of these things before you're seeing failures.
Yeah, exactly.
You've got predictive models, you've got ways to test things, you've got all these tools you can use to
make an informed decision.
Yeah. You don't have to wait for failure. To make a change.
Absolutely. You can do the science first, do the research first, and then come up with a design that makes sense.
That's right.
Yeah. And I guess that's what building science is. It's looking at the materials, looking at the variables on a building, and then designing the right thing. And I think the key funky thing is that there's not necessarily one right answer. There's probably 3 different opinions between the two of us, and any number of things can change how all of the components come together. So
that little Easter egg to the title of this podcast,
right? Exactly.
Yeah.
2 engineers, 3 opinions.
Yeah.
See you next time.